Hello, so welcome back to this series of prerequisite mathematics for machine learning ML. So today we are going to study matrices. Uh, yeah. So what is exactly matrice? So think of this screen, the one you are watching right now, the screen on your computer. Now there is like this white screen, there is this question mark, then there's how does a computer understand this image? This is the text. So you understand how does a computer understand this image, this text, but how does computer know what to show you and what to not? Like how does it represent the pixels and that what is this points exactly? Like what does it have to show? So it does so by Tada matrices. This is like a 1001. This is all like kind of you can think of it kind of a matrices working behind the screen that shows it that tells it ki what it has to run. So at its core, all the complex visual data which is in the image, it's just a massive grid of numbers and it is neatly organized into the rows and into the columns. So what you see here, it's all made up of matrices. So yeah, so this is that much important for to understand because after in ML, everything basically boils down into matrices. So matrix, what is a matrix? So matrices is just a plural term of it. So what is matrix? So it's a two-dimensional array of scalars. Scalars is just nothing but a fancy word for numbers or constants. So it is just a two-dimensional array matrix of scalars, which is with one or more columns and one or more rows. So this is just the layman definition. Definition is a bit different, but you can get the gist of matrix by just looking at this definition. So we'll just see some matrices. So matrix, this is a matrix, this is a matrix, this is a matrix, this is a matrix. So what is this? So what do we say in the definition? We said it should have multiple rows, one or more than one rows. So it has one, two, three rows, and it should have one or more columns. So it is a one, two, three columns. Here it is three rows, it is one column. Here it is one row and it is three column. Here it is two rows and it is two column. So in every aspect, you can see there is one and one or more rows and columns built. So this is exactly matrice. Uh, how do you exactly show this? So if I say this is an A matrix, then A matrix belongs to some A matrix has some element A on the ith row and jth column. So if you want to show this, you have to know that, and this is also represent A matrix as M cross N, where I belongs to 1, 2, 3 till M, and J belongs to 1, 2, 3, and N. So guys, you have to I have to apologize because this is not a perfect handwriting, but yeah, it's there. I'm just trying to write it perfectly for you. So yeah, so this is like the A M N. So M is the number of rows, which here it is one row through two row, three rows, and N is number of columns. Here it is three. So this is like A three cross three. So this is how you represent it. So now what do I mean by Aij? So Aij is the element in this matrix. So in this matrix, there are numbers in each of these spots. So how do you identify which spot is where, and how does computer know where to identify? So what it does, it goes by A of I and J. So first 1 comma 1. So A, it is one row and one column. So by row we go 1, so it is 5, and by column we go first, which is also 5. So this is our A11. Then let's say A21. So A21 is basically second row, first column. So first row, second row, this. Then 21. 21 is basically you have to go by this first column. So this. So 0, 0 is your 2, comma 1. Then let's say what is 3, comma 2. So it is third row, which is this, and it is second column, which is this. So it is 0. So this is how you represent it. So this is if this is 3 cross 3, then what kind of matrix is this? There are how many rows? There are 3 rows, and there is only one column. So it is 3 cross 1. In this, there is only one row, but there are 3 columns. So 1 cross 3. Here it is perfect 2. So 2 rows and 2 columns, 2 cross 2. So yeah, this is like the basic gist of the matrices, and like how do you represent them. I hope you all got it. Next we'll move to uh, there are some kind of matrices. This is just a form of a matrix, but you can also differentiate the matrices according to their units and all. So we'll get into that. So let's see the next. So the first is identity matrix. This is like the number one person of the matrices community. So how do you represent the identity matrix? So in normal matrix, there are different number A11, 12, 13. I told you this before. So these are all the elements of the matrices. But in this, elements can be of anything. But if the diagonal elements, which is like this diagonal elements are 1 and the rest of it all is 0, then it's a identity matrix. And identity matrix is something which is very important in algebra also, and linear algebra also, and in machine learning also, because tells us about it tells us about different properties of matrices, and it will come handy in inverse and transpose, etc., which we will know in the later part of the lecture. So this is, yeah, so this is np.identity3. So this is just a code for, like, this is just a syntax for to get the identity matrix. So you can also get np.zeros, then all will be 0. Yeah, so that is the identity matrix. Second is diagonal and triangular matrix. So first there are square matrix written here. So what is square matrix? So like I told you, in this there is something called A in m cross n. So m is number of rows, n is number of columns. So if m and n are equal, that is if m and n are 2, comma 2. So here it is like just 4 cross 4. So m and n are equal. So that is square matrix. And if there is a square matrix whose lower half is 0, but above this main diagonal, the elements are some non-zero numbers, then it is upper triangular matrix because upper numbers are present. And here, if there is a non-zero numbers on lower triangular region, then it's a non-triangular lower triangular matrix, and upper side there will be zeros. So what is diagonal matrix? Diagonal matrix is exactly kind of opposite of identity matrix. So you can say here the A11, 22, 33, 44. This is like a 5 cross 5 matrix, and in this, if you see, you can see the diagonal elements. They will be 1, and this will be all 0. So whatever like written here, A11, 22, 33, whatever you can write here, but here it is like just 0, 0, 0, 0, 0, 0, 0, 0. So if you can kind of say that this identity matrix is also diagonal matrix, but you can't say diagonal matrix is identity matrix. So that is not vice versa true. But yeah, the it can be said. So this is like a diagonal matrix. So then let's move on to the matrix algebra. So what do we say about the algebraic terms? So for addition and subtraction, you have to know that they must be of same size. Like the number of rows should match with the number of rows with the second matrix, and the number of columns of first matrix should match with the number of columns with the second matrix. If it is not equal, then sorry, you can't add or you can't subtract. So that will always be the case. Then the number of columns for the multiplication it is the matrix multiplication. For that, you need to have the number of columns in the first matrix. That is, if there is like a m n and there is b c d. So you have to match m with c and n with d. No, no, sorry. If the number of columns in the first matrix, which is like n, it should be equal to the number of rows in the second, which is c. So I'll show this to you in writing only. Let's move forward. So yeah, how do we add, subtract, multiply, whatever. So first, I'll tell you the syntax. So like what I said, you have to have same matrix. So if it is like 2, 1, 0, 2, 2, 2. If this is like what, 2 cross 3 matrix, then you also need 2 cross 3 matrix. Let's say it is 1, 1, 1, 1, 1. So you need this same shape to add. So if you add it, then the result will be something of 3, 2, 1, and 3, 3, 3. This will be your resultant matrix. But if you, let's say, subtract it, then your answer will be 2 minus 1, 1, 0, minus 1, 1, 1, 1. Yeah. So you can only subtract or add with this same sign. If it was anywhere like different, then it wouldn't have worked out. So let's say if this is not, this is like the 2 cross 3, and this is also 2 cross 3. That's why it's been working. Okay, so I'll show you later also how it works and how it doesn't work. That we will do by coding. But yeah, and also, there's a sweet syntax for it. Like you can understand this by Cij. Let's say this is A. This is A matrix. Let's say this is B matrix. Then your C matrix element Cij will be equal to Aij plus Bij. So for all I comma j. So I comma, this is the for all symbol and this is I comma j. So like if you add and subtract the same spots like 2, 1, this 1, 1. So you you kind of add and subtract the same spot elements. So yeah, this is like the addition and subtraction rule, and this is the syntax if you want to remember. So this is like A11, this is A12, this is A13, this is A21, this is B11, this is B12, this is B13. So this is like the syntax. Okay. Now let us move towards the scalar multiplication. So don't be afraid of scalar. Scalar is just a big word for the constant, which is number. So if you multiply any matrix by a scalar number, by a constant number, then you just multiply by the all elements of it. So let's say your scalar is alpha and your matrix R is, let's say, 5, 5, 1, 2. Then your R alpha, alpha R alpha anything would be something of 5 alpha, 1 alpha, 5 alpha, and 2 alpha. So you just have to multiply it by this. So think of this alpha as a volume button. So if alpha value is greater, the volume will be up. If alpha is late, if volume is lesser, then alpha's value is also lesser. So vice versa. So you can say this is kind of the scaling thing. That's why we say scalar multiplier. We kind of scale the matrices through this kind of operation if we want to scale it. So this has like a very good application in computer graphics and all. So whatever the rotation happens in the elements and all that all happens with this kind of operations only. Like if you want to scale something and you want to make it big in SolidWorks or in like any CAD software you can see. So that is like the scalar multiply. Then there is a matrix multiplication. So matrix multiplication is tricky, but it's very convenient actually. You don't have to do a lot of thing for that. I'll just write two matrices. This is A11, A12, A21, A22, and A31, A32. So there is a rule for this. This is what? Three rows, two column. Now I'll do a 0, 1, 1, 0. This is 2 cross 2. So according to our rule, the column of the first element, this, so I'll just column of this element and the row of this second element, they both should be same. So if this is 2, this should be 2. Otherwise, you can't multiply. This is the only important rule of the multiplication, and multiplication is very important, I will tell you. So this should be equal, and the resultant matrix, what you get is of 3 cross 2, the row and the column of the first and second. So this should be equal so that you can get a resultant matrix of this 3 cross 2, this one. So what will it be? How do you calculate this? So this will be 3 rows and 2 columns. So how do you do this? So you just what do you do? You just go this horizontally and this you go vertically. So let's say you should multiply the ith row of the first element with the jth row of that element. So jth column obviously. So I'll just write something for you. This is like a syntax. It's easy to remember. This is A, this is B, this is C. So there will be some C11, C22, C11, C12, C21, C22, C31, C32. So how do you represent that? You will represent it. You will represent it by uh, ith row of A, ith row of A, and you will do the dot product of it with the jth column of B. Okay, so ith row of A and jth column of B. So how do I say that? So ith is, let's say, 1 comma 1, C11. So C11 is basically this first row, and this is the first column. So A11 into 0, 0 plus A12 into 1, A12, A12. So this is your answer, A12. Then for the 2-1, so for C21, that is second row, first column. So for this, you go second row, which is this one, and you go first column this. So A21 into 0, 0, A22 into 1, A22. So this is like A22. You can also go A32. So for C32, you go third row. Third row is basically this 3, 1, 3, 2, and the second column. So this is 1, 0. So it is A31 plus 0. It's A31. So these are the all elements that should fit in here. So this is how it will be. So yeah, this is how you will multiply. So I can also give you an example if you want. Um, it's very Let's do the simple example. Let's do the square matrix one so it is easy to understand. So I'll do 5, 3, 3, 5, and I'll do 1, 2, 2, -1. Then the result will be a 2 cross 2 matrix because it's everything is 2 cross 2. So how do you go about it? You go 5 into 1, 5, 3 plus 2. So 5 into 1 and 3 into 2, 6. 6 plus 5, 11. Then you go this and this. So 5 into 2, 10. 3 into -1, -3, 7. Then for this, 3 into 1, 3. 5 twos are 10, 13. Then this 3 into 2, 6. And 5 -1 into -1 is -5. So 6 minus 5, it's only 1. So this is your like the multiplication. Yeah. So let's move ahead. This is just the normal uh, matrix multiplication. You can do it 2 cross 2, 3 cross 3, and etc. etc. Uh, you can also solve some examples if you found on Google or something to just get a bit of practice in it. That will be good to perform. In ML, we don't explicitly do this, but it's like in the code itself, it runs this. So yeah, it's kind of important thing. So it also has its law. So there's a commutative law. So in commutative law, you can say that A plus B can be equals to B plus A. There's also associative law that A plus B plus C. You can also add first A plus B and then C, or you can add A, then B, then C. You can also add B plus C first and then A. So this is like the associative law. It follows this law. It also follows the commutative law, which is A plus B equals to B plus A. You can like do the vice versa addition, it can work, but not subtraction. Okay, so you can do A minus B, but it should not necessarily be equal to uh, B minus A. Okay, so you have to understand that. And there's a property for multiplication also. There's A into identity matrix equals to identity matrix into A, because I is just what? It is like 1 cross 1. So it doesn't matter. It will basically be A only. Then associative law, you can first multiply B and C, then A. You can multiply A and B and then C, and or you can multiply by A, then B, then C. Whatever, it's fine. Then first distributive law, you can do the first add b plus c and then multiply it by a, or you can do the a into b plus a into c. There's also second distribution law that you can add after the brackets. You can also do the operation a plus b into c. So you can do a into c and a b into c. Okay, but there are some remarks about this. What are these remarks? What do we have to be worried about or like remark about? So AB is not generally equal to BA because the multiplication goes reverse for this. So it's not necessarily true. Then AB equals to 0. If AB equals to 0, that is 0 matrix, then neither E or B necessarily equals 0. So I can give you one example of this. So there is like one, this is like a popular example. You can just 1 0 0 0. This is not a zero matrix, right? This is not a zero matrix. Then 0 0 0 1. So what is its answer? Okay. So you go this and this. So 1 into 0 0 0 into 0 0. Then second, 0 into 0 0 0 into 0 0. Addition is also 0. Then 1 into 0 0 0 into 1 0. Then 0 into 0 and 0 into 1. So 0. So this is 0. So A into B is 0 matrix, but that does not mean A or B is 0. So this is one of a famous example. So you can see that does not always holds true. It's not necessarily that both or one of it will be 0. This is not a normal multiplication. Okay, so and then there is third, if A equals to AB equals to AC, then B is not necessarily equal to C. This is not like normal one when you can just be like if there is a 5 into 3 and 5 uh 3 into 5, then you can just not say that both are equal, that this you can cut. And because matrix multiplication works different, you can see from the earlier status also. uh Okay, then let's do the next, transpose and determinant. So what is transpose? Transpose is very funny, or it's kind of like a magic tool with the matrices. So you can do certain things with transpose and determinant, especially determinant. Transpose is also very useful. So I'll give you a plain example. Like this is like what? A M cross N is what we have studied. uh, we got this answer that A M cross N is basically what A I comma J for I equals to 1 2 3 M and J equals to 1 2 3 N. Then what is transpose? Transpose is basically A J comma I. You just have to substitute the rows into columns and columns into rows. So this goes like N cross N. So example, let's see it by example. If I want to say this, then I'll just say uh, if this is 1, 2, 3, 4, 5, 6, this is the matrix A, then A transpose, it will be something of a 1, 2, 3, 4, 5, 6. So what was this? This was 2 row and 3 columns. Now what do we get here? 3 rows and 2 columns. So this is like the A transpose, and it has particular properties. It says if A plus B transpose, you can do A transpose separately and B transpose separately. If both are multiplied by transpose, then B transpose into A transpose. You can't do this A transpose into B transpose. This is like the reverse thing. Then K into A transpose, so you can have K separately, and then that it is A transpose. You can just multiply this. So it is a scalar value K and A transpose of transpose. So basically, if you reverse this, then it will become this same A element. So A transpose is basically A only. Then every square matrix has a determinant. Square matrix, I told you, it is a kind of a like n is equal, and that determinant is a number. So whatever, think of it like the value of that determinant, because you can't make sense out of this box, right? If this is given to you 1 2 3 4 5 6, you will say what is this, you don't it doesn't make any sense. So determinant kind of finds the value for you, which decides lots of things, which we'll cover later, of course. But just think of it as something important, some important number, some summary it gives to the that matrix. Okay, and the determinant you can calculate. Just let's see, if there is 2 1 3 and 1, then you can just calculate it by this cross multiplication. So 2 into 1 2, 3 minus 3 into 1 3, so it's -1. So the number could be negative, positive, 0, anything. It depends. Generally, if the determinant is 0, then it is called a singular matrix. And if it is a singular matrix, then you can't actually get its inverse. So, what did I say? What is inverse? It sounds very scary, right? But it is not. Trust me, it is very easy. What is inverse of a matrix? So, consider a point K. Let's say, consider a scalar K. So, if let's say K is 7. So what do we say for its inverse? Inverse will be 1 by 7, right? If I do 7 into 1 by 7, I should get 1, right? So do this same kind of thing for matrix, but in matrix we can't have this 1/7 exist. So what do we say? We say A inverse equal to A inverse A equals to I. So this is A inverse. We don't write it as 1 upon A matrix because that is not like that you can't do the operation on that 1 upon A matrix. So we just say it is A matrix. So this A matrix can be of any value, and whatever this value is, it if multiplied with A will give you an 1 which is identity matrix. So it can be, if this is a 2 comma 2 matrix, then it will be like 1 1 0 0. So whatever matrix gives you the identity matrix for A, then that is A inverse, and that is also like vice versa is also true. So A is also the inverse of A inverse, and A inverse is inverse of A. That is like factually true. So yeah. Um, this is properties of inverse of matrix. So if A into B is inverse, you can calculate as B inverse into A inverse. Inverse of A inverse is basically A. And the transpose of A is inverse is basically A inverse is transpose. So yeah, and then K into A inverse. So if both are into inverse, then K you can do normally by 1 by K. And for the A inverse, you have to have this A inverse only. Now, another point to consider is square matrix has an inverse is called as non-singular matrix. So I told you, if the determinant of a matrix is, let's say, not zero, then it is non-singular matrix. If it is non-singular matrix, you can find its inverse. Its inverse can be found, yes. But if the A matrix has a determinant zero, then you can't find its inverse. Sorry, then you don't have its inverse. And it makes sense, right? Because if this is zero, then 1 upon A is 1 upon zero. So how do you define 1 by 0? You can't define, right? So basically, this does not make sense. That's why it like this whole thing you can't do have that for the matrix. That's why you'll have this kind of rules. Then square matrices have inverse except when the determinant is zero, which is I said. Then when the determinant of matrix is zero, matrix is singular. If this is zero, then it is not. You can't calculate inverse, but it's a singular matrix. Okay. Then matrix is singular. Okay. Now let's get to some coding part. So we'll have the coding part now. So it's easy to do this in coding actually. So whatever I said, whatever I explained to you today, don't believe me. Okay, I'll say don't believe me. I'm not that trustworthy, but you can trust computer, right? Computer won't lie. So let's get this. Where can I? Hmm, but I think I'm having trouble. Okay, so I stopped sharing right now. I'll just, yeah. Okay. How do I share? How do I share? Okay, I can share. I can share. Okay. So yeah, I'll, you might be seeing the code one. Then let's get into some applications. Let's get A equals to okay, I have to input numpy. So I told you earlier also there is a numpy library which we will use extensively. Then A equals to np dot array. So what you do is you just get this in array, and then you can have multiple arrays. Okay, so for me, I'm making this 2 rows, 1 comma 1, 2 comma 2, 3 comma 3. Okay, and then uh okay, I did something wrong, I guess. Yeah, I did not put commas here. Yeah, so now print 8. This is your 1 1 2 2 3 3. So this is your 3 comma 2 3 x 2 matrix, 3 rows, 2 columns. If I'll have the same for B, and I'll put the elements something different. Not that different, but little bit different. Okay, then. Oh, okay. I changed this. Okay, right. I changed. I'll do this B. Okay, so now will start with the adding thing. So let's C equal to be np dot add, and then I'll put A cross B. Okay, and then I'll print C. So you can see 1, 2. So this is 1, this is 2, this is 0 plus 2, 2, 2 plus 2, 4, and 1 plus 3, 4, and 0 plus 3, 3. I can also np dot subtract. So I will do this by d equals to np dot subtract, and then I'll print d. So you can see, so 0 minus 1 minus 1, 1 minus 1 0, 0 minus 2 minus 2, 0 2 minus 2 0, 1 minus 3 minus 2, and 0 minus 3 minus 3. So yeah, so this is like add subtract. We can also find the dot product. So I'll do E equals to np dot what A comma B. Then okay, yeah. So see, this is 3 comma 2. Uh, what is this? This is like 3 comma 2, and this is 3 comma 2. So if it is 3 comma 2, then the column of the first does not match the row of the second matrix. So we can't have that. So what I will do is I'll just change this to uh, 2 comma 2. So let's have E, and we'll add A and E. And in E, we'll have just 2 comma 2 matrix. So it will be easier to do the multiplication. Okay. Now I'll just do the np dot A comma E. Let's see the result now. Print E. See, 0 2 0 4 0. So this was the first was 3 comma 2, second was 2 comma 2. So result should be 3 comma 2. So 3 is third 3 rows, and 2 is 2 columns. So you have the result, right? Now this is like the matrix multiplication. You can also do the thing called, like, I'll just do this 3 cross E. Then it will just scale this by 3. So 3 twos are 6, 3 fours are 12, and 3 ones are 3. So yeah. So you can also do the scalar multiplication. Then we'll find the determinant. So for determinant, we'll do m equals to, okay, m equals to np dot array. Let's do 8 3 8. Then the second, let's do 3 6 3. And then third, let's do 5 9 5. Okay, so this is our m. Now to get the n, we will do n equals to np dot that this is linear algebra, and then we'll have to calculate the determinant. So determinant of m, and then we will print the n. So it's 0. So determinant is 0. So if it is determinant is 0, it does. What do you think? Does it have singular matrix, or is it singular, non-singular? Does it have inverse, or does not have inverse? So if a determinant of a matrix is 0, then matrix is singular, and you can't get the uh, inverse of it. So let's try if we can get the inverse of this. Np dot inverse. Np, no, you can't. So for inverse, you have to do by linear, then n. So see, array must be at least 2 dimension. I think. Okay, so this is just okay. I'll have to do this m. Yeah, so see the last line, what does it say? It's singular matrix, so we can't do the print this. So let's print this for A maybe. A array must be square. So you need to have this square. So what do we have? What do we have? Let's do E. Can we have for E? No. So let's print one matrix and P dot array. So let's quickly clear this. Okay, let it be P equals to NP dot array, then this, let's do 2 comma 2, and then let's have another 1 comma 0. So this is like a square matrix. Then we'll do the inverse of P. So if the matrix is not non-zero, then you'll have some kind of thing for this. So let's print P. So yeah, so this is the inverse. So if you multiply this with this, then uh you'll get the identity matrix, because A inverse of inverse is A inverse into A equals to I. So yeah, this is the whole part. I hope you have liked this. So in the next lecture, we will go through that inverse matrix. No, inverse is over. We'll go through that vector space sub topic, which we haven't covered. We have only covered the basics, and we'll try to finish this linear algebra sooner, so that we can go ahead with another topics which are really interesting. So yeah, I hope you like this content with the coding part. And yeah, okay, so stop sharing. Thank you. Yeah.